Okay guys, in this video we're going to look at solving another system that has three variables involved with it, but the very first thing I want you to notice is that this is a system that has three variables but only two equations. And so the first thing that I always want to acknowledge is this: a system can only ever have a single unique solution if we have as many equations as we do variables. So what is the implication then if we have fewer equations than we do variables? And so what I want to do is I kind of want to interpret this graphically here, but I want to recall that when we graph these equations that have three variables and they're all to the first power, what we're really doing is imagining that they are these two-dimensional planes that are graphed here. And so considering the fact that if we have only two equations here, then I can only ever have two planes. So graphically speaking, we would be looking at something that maybe looks like this here, have a single plane, intersecting with, say, some arbitrary second plane, but the idea is going to be that they could potentially intersect along this line of values right here, which is going to imply that we have infinitely many ordered triples that lie along this line of intersection here, and we're going to have to name all of them. Okay? So going into this, what I want you to understand is that we already know that we can't get a single unique solution because I only have two equations, but I have more variables than I have equations. Regardless of that fact, though, we're going to try to put this into what we call row echelon form. Certainly, this idea that if I have a system here and I wanted to solve it, that I could get this stair-step pattern going on here, where each row has a leading one as a coefficient, and each consecutive row has one less term than the row before it. And so making it look like this always involves by getting a 1 in the top left corner first. That's what we want to do. And so in this particular instance, I'm not going to treat this like any other treat it differently because it doesn't look like our other systems with three equations. I'm still going to get a 1 in the top left. And so it looks like we already have a 1 in the top left. Recall then that we're going to use this 1 to try to cancel out any variable terms below it. And so the real question is, what could I take times this positive 1 to get to cancel with my positive 4? And so, of course, the opposite of positive 4 would be the correct response. We'd say, I'm going to take my entire first row times negative 4, and I'm going to add that on to this second row right here. So what this means is, first of all, that our first row, even though we took it times a negative 4 and added it to row 2, it doesn't change. As a matter of fact, it's always going to stay the same as long as it has a leading 1 there, and we're using this type of elimination. Now, if I were to take negative 4 times this x, I'd get negative 4x, and negative 4x plus 4x would be 0. So effectively, we've canceled out this term underneath our x here, but we also have to go negative 4 times everything in the first row and add it to all of these second row entries. So we would say negative 4 times a negative 2y would be a positive 8y, and a positive 8y plus a 0 would be a positive 8y. So let me switch out my colors here. We'd say I get 8y. Negative 4 times a positive 5 is a negative 20, and a negative 20 plus this here is a negative 1 is be negative 21. So negative 21z. And then lastly, we're going to say negative 4 times this 2 right here in row 1 would be negative 8, and that negative 8 plus the row 2 entry 0 is negative 8. So what we end up with is this new row equivalent system that is not quite yet in row echelon form. And the reason why I say that is because certainly we have a 1 on the top left and nothing underneath it, but now my second row also needs to start with a leading 1. That's the rules. So if that's the case, then what we could do is we can multiply the whole second row by the reciprocal of this leading coefficient, because anything times its reciprocal is always going to give us a 1. So I'm going to list exactly that. We're going to take the whole second row times the reciprocal of this leading 8, so 1 over 8. And again, we produce a new row equivalent system where, again, the first row is now the same thing because we have a leading 1 there already. The second row now is going to become 1/8 of 8, which is 1, so 1y. That's what we wanted, was a leading 1. But I also have to say that this is negative 21 over 8z. And I also have to divide by negative 8 by an 8, or multiply it by an 8, however you want to look at it, but I get negative 1. So what I'm going to do is I'm going to put a box around this, and I just want to point out that this thing is in row echelon form. And the way I can recognize this is because each row starts with a leading 1, and I sort of have this stair-step pattern as far down as at least I'm able to carry it. So when we have systems with fewer equations than variables, you're always going to end up in this kind of situation where I can't carry out my stair-step pattern because I don't have the third equation to do it. So because we have infinitely many solutions, what we always tend to do is then we say, let's choose a variable. It wouldn't matter which one of these variables I choose, but I'm going to choose z here and allow it to be equal to a real number a. And we tend to often choose the very last variable in order, or at least to call some real number a. So if I'm going to call z equal to a, the very first thing I'm going to acknowledge is this then. My solutions, of which there's infinitely many, are some ordered triples, but I do know this. My z value has to be a by the way I'm defining it over here. Now, in a normal situation, let's assume that I knew what z equaled. Well, what would I be doing to find out y and x? Well, first y, what I would be doing is I would be plugging this back in for z. So I'm going to drag this equation off on the side. We had y minus 21/8 z equal to -1. And we're just going to make a substitution for z, replacing it with a, because we've allowed z to be equal to a. So in this case, we're still going to solve for y, but it's going to be in terms of a here, meaning that I'm going to have to add 21/8 a to both sides, so plus 21/8 a. Wouldn't even really have to show that, but I did want to show it. We get y equals 21/8 a minus 1. Now I'm going to put a box around this, and immediately I'm also going to go up here and say, well, you know what this means then? It means 21/8 a minus 1 has to be our y value here. And so, as we normally do after discovering z and y and doing back solving, we're going to take both of these values now and substitute them back into this primary equation, the first row equation, to go solve for x. So again, I'll drag my equation over here just so we can see it all in one place. X minus 2y plus 5 times z equals 2. And so we're going to have to do quite a bit of simplifying here, but we should be able to find x in terms of a as well. So substituting, we get x. Let me switch back here. X minus 2 times y, which in this case is 21/8 a minus 1, plus 5 times z, which we're just calling z equal to a here. This is equal to 2. So as far as simplifying goes, we do need to do distribution first here. So we're going to distribute. If I took this 2, -2, and multiplied by 21/8, I know that my 2 and my 8 would cross reduce. This would become a 4. This would become a -1. But I would get -1 times 21 over 4. In other words, -21/4 a. And I also have to take this 2 here, which, by the way, still does exist. I have to take it times my -1. So I get positive 2. Now that is still plus this 5a that we had right here. And this is all still equal to 2. So my goal here is going to be this. First of all, combine like terms. I notice that I'm going to need a common denominator here between fourths and wholes. So let's change our 5/1 into quarters, or fourths. So we'd have to multiply the top and the bottom by 4 here, meaning that we get a new expression, x minus 21/4 a plus 2 plus 20/4 a is 2. And if I were to put -21/4 with +20/4, we should just get a -1/4 a, and this is plus 2, and this equals 2. So now the only thing I'm responsible for doing is now putting these to this side. So that means I would subtract 2 from both sides. As a matter of fact, if I subtract 2 first, just to show you here, this is kind of cool, I would get 0 on the right because those would cancel out. And then I'd still have to add the 1/4 a over, so I get 1/4 a. We'll put a box around this. But it means that I've found my x value in terms of a. Now, what is the significance of the solution right here? Well, what I want you to know is this is actually the ordered triple of every single point along this line of intersection. And so it looks kind of weird to interpret them in terms of a. So what I want to do is just really quickly here, I want to assume if a were equal to 0, what would be the actual ordered triple? And so I would have 1/4 times 0, which is 0. I would have 2/21/8 0 minus 1, which is 0 minus 1, which is -1. And I would have just 0 for this a here. I want to check to make sure this works. So what I'm going to do is I'm going to plug this back into my original system's equations to make sure that it does work. And so what I notice, I suppose, is in my first equation I'd get 0 minus 2 times -1 plus 5 times 0. And this should come out to equal 2, but that makes total sense given that those products are 0 and -2 times -1 is 2. So it satisfies the first equation here. And if I were to kind of try to give myself some room here, maybe I'll do it up here. If we were to plug in now 0, -1, and 0 into the second equation, we would get 8 times -1, which is our y value, minus, I'm looking at the wrong system here. We need to be going off the original equation. So we'd say 4 times 0. We don't have a y value to plug this negative 1 in for, but our z value here, we said minus z is 0. We get 0. So in other words, we get 0 minus 0, and 0 equals 0. So this is just one point that would satisfy both equations in the system. If you were to go back now and substitute in a different value for a, and I would encourage you maybe to try this, what I might suggest you plug in for a is, say, 8, because 4 is a multiple of 8, and 8 is a multiple of 8, and you'll get your denominators to cancel easily when you plug in an 8. But you'll see you get some new ordered triple that when you plug it back into the system again, still works. So we're going to tend to leave our systems that are infinitely many solutions as this, and we'll always assume that we allow our last variable to equal some real number a, and then we will back solve into our system as we traditionally do when we have as many equations as we do variables. Cheers.